Welcome. In this video, I'm going to go over the solutions to the Paper 2 exam given in May of 2016 for SL Chemistry. Question 1, phosphine is a hydride of phosphorus with the formula pH3. Draw a Lewis structure. So you should remember that phosphorus has 5 valence electrons and 3 from each hydrogen. So that means I'm going to end up with the 3 hydrogens single bonded and a lone pair on the phosphorus. Outline whether you expect the bonds in phosphine to be polar or nonpolar. And you would expect them to be polar because they're 2 different atoms, but if you look at the electronegativities, it's 2.20 versus 2.19. So technically polar, but just barely. And so, in fact, in most cases, we would consider this nonpolar because there's such a small difference in the electronegativity. Explain why the phosphine molecule is not planar, and that's because there is a lone pair forcing the hydrogen closer together. And when it forces them closer, it takes them out of the plane. Number 4, phosphine has a much greater molar mass than ammonia. Explain why phosphine has a significantly lower boiling point. So phosphine is pH 3, and as we looked at, it's got very low polarity in the bonds, but NH3 has really high polarity, really polar bonds, so polar that they're considered hydrogen bonds, and the hydrogen bonding is going to greatly increase that boiling point for ammonia. Part B, it's usually prepared by heating white phosphorus, one of the allotropes of phosphorus, with concentrated aqueous sodium hydroxide. The equations below identify one other element that has allotropes and list 2 of its allotropes. So carbon and oxygen are the 2 common ones used. And for carbon, allotropes would be diamond, graphite, and there's actually a third one of fullerene, or Buckminster fullerene. And then with oxygen, it's O2, or oxygen gas, and then O3, or ozone. Part 2, the first reagent is written as P4, not 4P. Describe the difference. P4 is bonded, so perhaps like so, unlikely to be a ring, but the idea that all 4 phosphorus are bonded, whereas 4P are 4 separate atoms. The ion H2PO2- is amphiprotic. Outline what is meant by amphiprotic. Given the formula of both species, it is converted to when it behaves in this manner. So amphiprotic means it can act as an acid or base. So it can gain or lose hydrogen. So if it gained hydrogen, it would become H3PO2 and lose that -1 charge. Or if it lost another hydrogen, it would become PO2, with a -2 charge. Part 4, state the oxidation state of phosphorus in P4 in an H2PO2-. So P4 is elemental, so that's going to make it 0. H2PO2-, I have 2 hydrogen at a +1 each. I'm not sure of my phosphorus value. I've got 2 oxygen at a -2 each, and the total charge is -1. So I have a -4 here, a +2 here, and I need my overall charge to be -1. That lets me know the phosphorus is going to be +1. Part 5, oxidation is now defined in terms of change of oxidation number. Explore how earlier definitions of oxidation and reduction may have led to conflicting answers for the conversion of P4 to H2PO2- and the way in which the use of oxidation numbers has resolved this. Well, the old definition is that oxidation was defined as the gain of oxygen, and reduction was the loss of hydrogen. So this would be a confusing definition to use here because H2, in this case, P4 is gaining both hydrogen and oxygen, which it appears that there should be one gaining oxygen and someone else, another species, losing hydrogen. And in this case, P4 is involved with both the hydrogen and the oxygen. So the oxidation numbers make it really clear that it's really the transfer of electrons and then the accompanying change in oxidation number, or shown with oxidation states, where that control is being gained and lost of the electrons. Part C, 2.478 grams of white phosphorus was used to make phosphine. Calculate the amount in moles used. So I've got 2.478, and the molar mass is going to be 4 times 30.97. So that gives me 0.01994 moles, if I stick with my sig figs here. And then continuing on part 2, I have 0.1 liters of the NaOH at 5 molar. So that means I could make, I've got 0.500 moles of the NaOH, but it occurs in a 1:3 ratio with the pH3. So I can make 0.167 moles of product, or pH3, from the NaOH. With the P4, I have 0.01994 moles of the P4, and it occurs in a 1:1 ratio, so it's going to make 0.01994 moles of P3. So that means my P4 is my limiting reactant, making quite a bit less product. So to determine the excess amount in moles of the other reagent, there's a couple ways I could do this. I could take the 0.167 moles of pH3 that I would expect my NaOH to make, and I can subtract the 0.01994, or 0.020, and I realized I should have 0.147 more moles of pH3 I could make. So when I convert this back at a 3:1 ratio, that lets me know there'd be 0.441 moles excess of NaOH. I could have also taken the 0.02 and taken it times the 3:1 ratio to say 0.06 used, so 0.5 minus the 0.06, and I again would have gotten the 0.44 of NaOH left. Determine the volume of phosphine measured in centimeters cubed at standard temperature and pressure. Well, if I'm getting 0.01994 moles at STP, then I know that should be 22.4 liters per mole at STP, which gives me 0.447 liters, or 447 centimeters cubed. Part 2, they talk about impurities, and then they give you a bunch of data there, and they want to know what's the temperature rise using section 1 of the data booklet. So I know I have 1 mole of pH3, and I see that I get 750 kilojoules per mole. So 1 mole of pH3 times the 750 kilojoules per mole released means there'd be a negative 750 kilojoules of energy being released. And I know that this 750 kilojoules was being released by 2 grams, or 0.200 kilograms, or I could change the 750 back to joules. Either one would work. And my C value is going to be 1. And then I can find the delta T from this. So I come up with a T value, or change in temperature, of 3,750 Kelvin. Part 2, the oxide formed in the reaction with air contains 43.6% phosphorus by mass. Determine the empirical formula of the oxide. So if it's 43.6 grams or percent, 43.6 grams out of 100, and I know 1 mole has a mass of 30.97 grams, we're really talking 1.41 moles of phosphorus here. And then that means the other 56.4 grams is oxygen, and 1 mole of oxygen is 16, giving me 3.525 moles. And when I divide this, each of these by 1.41, I get P1 and I get O equal to right about 2.5. So really we're talking P2O5 is the empirical formula. The molar mass of the oxide is approximately 285 grams per mole. What's the molecular formula? Well, P2O5, if I take 2 times the 30.97 and 5 times 16, I get right around 142 grams per mole. Compared to 285, that's only half as much, so I would double this to P4O10 for the molecular mass. Part B1, state the equation for the reaction of this oxide of phosphorus with water. So if I have P4O10, I'm going to expect it to behave acidically with water and form H3PO4. And to balance that then, I'm going to need a 4 here and a 6 here. Part 2, predict how dissolving an oxide of phosphorus would affect the pH and electrical conductivity. The pH will decrease, and they're just saying predict here, so I don't have to give any explanation. It's going to decrease, and the electrical conductivity will increase with the influx of the H+ ions. Number 3, suggest why oxides of phosphorus are not major contributors to acid deposition. Phosphoric acid, remember, is a weak acid, not strong like HNO3 or H2SO4, which are the main contributors to acid deposition. And then the last part of number 2, the levels of sulfur dioxide can be minimized by either pre-combustion or post-combustion methods. Outline one technique of each. So pre-combustion, I don't know if you consider this a technique so much, but use low content coal. You can crush the coal and wash it with water. And you can use a process called HDS, which combines refined petroleum with hydrogen to form H2S. Post-combustion, they usually use some kind of desulfurization technique, like using a wet slurry of calcium oxide and calcium carbonate to form calcium sulfate. And remove that from your exhaust or from your discharge.